So hello everyone. I'll talk about the height function transformation of minimal surfaces. I want to thank the organizers for giving me this wonderful opportunity. So let's start with the definitions. A function f from omega, which is an open subset of R2 to R, is said to be a minimal graph surface if its graph will form a minimal surface in E3. But for our purposes, it's the solutions of this minimal surface equation, equation 1. There are many examples for minimal graph surfaces. They are the planes, the helicoids, the catenoid, the Scherk surface, the Scherk second surface, etc. So let's come to the main object of this talk, which are the minimal graph transformations. So what is a minimal graph transformation? A map G, which is a map from U, which is a open subset of R, to R, is said to be a minimal graph transformation if of a particular minimal surface, if f of omega is a subset of U and the composition is again a minimal graph surface. So a minimal graph transformation transforms the height function of a minimal surface into height function of another minimal surface. And there are mainly two types of minimal graph transformation. The first is the trivial minimal graph transformation, which or TMG transformation, which transforms every minimal surface into another minimal surface. Then the second is the non-trivial, which by definition it's just a transformation is non-trivial if it is not TMG transformation. So the problem statement is basically explicitly find all the trivial minimal graph transformation and the non-trivial minimal graph transformation and their corresponding minimal graph surfaces. So first let's roll out the trivial cases. So you have minimal graph transformation, then the trivial cases are precisely the trivial minimal graph transformation and the constant minimal graph surfaces. So you have trivial minimal graph transformation, which are precisely the transformation which transforms every minimal graph surface into another minimal graph surface. And it can be shown that that happens precisely when the G prime cube minus G prime is equal to 0. In other words, it's just a constant function or translation function or reflection plus translation. Now you have the constant minimal graph surface. So this comes in the question where you ask, for what minimal surfaces does every smooth function is transformed into another minimal surface? So that's what we answer in this particular thing. It can be shown that the only minimal graph surface for which every smooth function is again a transformation is precisely the constant minimal graph surfaces. So that means the f of xy is equal to c. Okay, now let's come to the non-trivial case. So you have done the constant minimal graph surface and the trivial minimal graph transformation. Now let's talk about the non-trivial minimal graph transformation of non-constant minimal graph surfaces. So that leads to two equations, the minimal surface equation and the Laplace f by grad f square is equal to h of f condition. So how do we get that? So you apply the basic formula and then you will get this equation 2. And then the h will be called as the first characteristic function of the non-trivial minimal graph transformation problem. And then from this h, one can actually find the minimal graph transformation using the equation 3. Okay, now let's assume that the first characteristic function h is 0. So in that case, one can see that the minimal surface corresponding to that is precisely the helicoids and the planes, and the transformations is precisely a parameter change. So what I mean by that is, so how do we do that by converting the xy to z and z bar coordinate, and then applying the fact that h is equal to 0, you will get this system, and explicitly solve it, we'll get that it is the helicoids and the planes, and the minimal graph transformation is given by g of t is equal to at plus b, and it transforms a helicoid into another helicoid, but with another parameter, and a plane into another plane. So this is an expression picture for helicoid. Okay, now suppose that the first characteristic function is non-zero. So in that case, one can actually transform this system into an equivalent system, into a different system with a different set of functions, the u and j. But here the quality, here the importance is that the Laplace u is equal to 0. So it's a harmonic function. So what we do is we just transform the system into a different system using these parameter changes, and then we'll get the system 5. So this is system 5 will be known as the modified non-trivial minimal graph transformation problem, or modified NMG transformation problem, and the equation J, the function J will be called as the second characteristic function of the NMG transformation problem. So we have two systems, one with F and H, and another system U and J. So it can be shown that these two systems are equivalent. So what do I mean by equivalent? If you have a system, if you have the system F comma H, you can do the transformation and get a system U comma J, which gives you the solution for the modified NMG transformation problem. Similarly, if you have U comma J, the solution to the second system, one can inverse transform it and get the system F comma H, where it gives you the solution of system 1. And if you have that system, one can do the transformation again to get U comma J again, at least in a smaller neighborhood. So our quest transformed to solving the first system to the modified system. So yeah, now you have the modified system. What you will do next? You apply a technique called weakening technique, in which you transform the second system, the modified system, to a simpler equation. In fact, a complex ODE given by this. It will be called as the weakened equation. So how do you do that? You have that U is harmonic, so it is basically a real part of a holomorphic function. So it can be given by A of Z plus A of Z bar, A of Z the whole bar. Now apply that fact to this modified system, you will get this equation. Now we will apply a weakening technique, which what you will do is basically you have J of U, you differentiate with respect to Z and Z bar, and you multiply. So if you do, when you differentiate with respect to Z, you multiply it with B dash Z bar, where B dash Z bar is given by the A of Z the whole bar, and when you differentiate with respect to Z bar, you multiply it with the A dash of Z, and we see that the results are basically same: J dash of U, A dash of Z, B dash of Z bar. They both are same in this, and hence we'll do the same thing over the left hand side to get this equation 6, which is called as the weakened system. So differentiation process yields a weaker system, so it may admits more solution. So our strategy is to solve exhaustively and get and check whether it satisfies the modified system or not. So we have three cases: k greater than 0, k is equal to 0, and k less than 0. It involves a lot of elliptic functions and elliptic integrals. So I will not go into the details of this calculation, but I will present the exact solution. So for k is equal to 0, we get the Scherk surface, a very famous minimal surface, and we get that the NMG transformation is precisely parameter change. So you have the Scherk surface, you transform it to another Scherk surface with a different parameter. So this is the Scherk surface equation F, and G is the equation for transformation. So this is a figure for Scherk surface. Okay, now let's come to the second case, k greater than 0. In this case, you will get a new parameter C naught, and in C naught, with that you will get another minimal surface, which is the catenoid, and we find that the transformation are precisely parameter change. So F is the catenoid, and G is the transformation. So this is a picture for catenoid. Yeah. Now let's come to the next case when C naught is not equal to 0. Here you will need a elliptic integral. You need to solve an elliptic integral, and you will find a new family of minimal surface, which we will name as the pillars. And we find that the transformations are precisely again parameter change. So this is the equation for pillars, and this is the equation for transformation, and you have the Cn and Sd as the elliptic function. So this is a picture of the pillars. Yeah. Okay, now let's come to the last case where you have k less than 0. Here you will get a parameter 2c0 by mod k minus c1 less than 0 is equal to 0 and greater than 0. For the less than 0 and greater than 0, you will get an elliptic integral to solve. And when you solve that, for is equal to 0, you will get a normal integral. You will get three type of new families of minimal surface. The first one is called the sharp walled, and the second one is the great wall, and the third one is the thick wall. And the transformations are precisely given by, for the thick wall, you have a parameter change transformation, and as well as a transformation which transforms thick wall into sharp wall, as well as the great wall. Similarly, for the sharp wall, you have a parameter change transformation as well as the transformation which transform it into thick wall as well as the great wall. Now, for the great wall, if it to be a NMG transformation, then you only have two types of transformation. You do not have a parameter change transformation. So these are the equation for the these minimal surfaces, and the picture of the great wall is the thick wall, the sharp wall, and the transformation for the great wall is given by these two. There is only two type of transformation, and for the thick wall you have three types of transformation, and for the sharp wall you again have three types of transformations. Yeah, so these are the references. Here, the first one is the reference for this particular talk, and this is motivated by the second reference where they transform the Gauss-Codazzi equation of a minimal surface into Gauss-Codazzi equation of another minimal surface using some algebraic techniques. Thank you for listening.
Any questions?
I cannot understand. You have mentioned a term as height function. What is height function?
So here the minimal graph surface is precisely given by x, y, f of x. So in that case, the height function is precisely f of x. So here you assume that f of x as you call f of x as the minimal graph surface. So that's why transforming height function is giving you the minimal graph transformation.
The minimal surface is given by your height function.
Yeah, it can be given by me.
Thank you.
Yeah.
Any other questions? Not, let's thank the speaker.
So when we were getting these non-trivial transformations, you get this h of f, that function. Like, is it like some arbitrary function, or like how do you?
Yeah. So so basically, h is. I will go to that. Yeah. So if you need to, if your minimal surface is to satisfy a transformation, then it should obey this equation for some h, and that h cannot be arbitrary. That's what we'll show. It has a relation with the transformation. So once you have h, that corresponds to a transformation, and that transformation cannot be anything. It can be. It should. As I show, it is precisely of these forms. So h is also fixed. And we'll solve it. When you solve this equation, you'll find those.
It sort of dictates the kind of transformation that we are doing.
Exactly, yeah.
And also, like this sort of similar analysis, does it exist for other extremal surfaces, like maximal surfaces?
Maximal surfaces. I believe that you can do that. It's more or less similar, but I don't know. Maybe for some reason there can be some difficulty. At least for the Bonin field type of, where you have the metric to be 1, -1, and 1, there you have to do this analysis in split complex number, which is basically I square is equal to +1, not -1. So those kind of difficulties can arise.
Thank the speaker.